This part of the lecture is concerned with the question of what gain estimation is. What is the gain and why do we need to estimate it? So let us imagine that we have our CMB experiment represented by this expertly designed detector, which is pointed at the CMB. The CMB at all points of the sky has an intensity or a temperature. We can represent the intensity in terms of a CMB temperature as well. And the task of our experiment basically is to accurately describe the intensity at each point. So we can imagine that this detector is pointing somewhere, and we want the detector to tell us what is the intensity at this point. Would be great if the detector told us this directly. Unfortunately, what we get out of the detector, because how it works typically is that you have photons that are hitting the detector, and these photons induce a current, and then that current is described by a voltage. And so there is a correspondence between the intensity that the detector is at the point at which the detector is pointing and the voltage that we read out at that time. And if you design your detector in a way that makes sense, you try to make this a linear relation so that whenever the intensity increases, the voltage increases as well. And the constant of proportionality between the voltage and the actual true intensity is what we call the gain, this G factor right here. And so the task of gain estimation is basically to try to figure out what this G is. As you can imagine, if we get this G wrong, we will get almost every other aspect of the experiment wrong as well. The foregrounds, the CMB, temperature, everything will be off unless we can get this factor to be right. And that doesn't seem like it should be very difficult. We can even do this back on Earth. Can't we just, shine a flashlight at our detector, which we know basically the intensity of, and then read out what the voltage is, and then it's a very easy system to solve for G. But the problem is that G, the gain, is a function of time. So even if we were to measure it on Earth, once it got up in space, the gain would vary. And so the problem of gain estimation is a lot more subtle than just having to estimate this once. We have to estimate it continuously during the whole mission. And this is the task of gain estimation. So this part of the lecture will be about some initial considerations about the gain estimation process in order to try to build a bit of intuition of why we're doing what we're doing. As I mentioned earlier, the gain is a function of time. So it's free to vary. And if we write down a crude data model which works for our purposes, we can say that the detector, the readout that we get from the instrument, the actual data that we're working with, which is given in volts, is given by the gain factor, which can vary in time, times the actual sky signal. There are a bunch of convolutions going on inside of this equation, but let's just keep it simple for now. The sky signal can also vary with time because the instrument is pointing at different parts of the sky at any point in time. And this is the true sky signal which we're after, which we're trying to find, basically. And that's given in intensity units like megayansky per steradian, or Kelvin, or whatever. In addition, we have some instrumental noise. This is typically a sum of white noise and correlated noise, which then must also be given in volts for this to make sense. But what we can read from this equation is, first of all, that this system looks to be very degenerate. If the noise and the gain is allowed to vary in time, and the signal, we have some problems. The signal is typically constrained because we are in the Gibbs sampling context, which means that the signal is actually perfectly known as we get to the gain estimation step. The noise, however, is free to, or is partially free to vary. The white noise part of the noise is not completely determined. And so this means that if the gain is free to vary and the noise is free to vary without constraints or without any other knowledge, then these are completely degenerate. If we look at our data and we see some variations, it's impossible to tell whether this is due to a noise fluctuation or whether this is an actual change in the gain. And so we have to try to look for ways to break the degeneracy between the noise and the gain itself. And one of these assumptions is that G is slowly varying. What slowly means here is basically or that can vary from experiment to experiment. So what we are assuming is that the gain is varying on scales that are longer than typical noise fluctuations. And this turns out to be not such a bad assumption. It is true that the electronics of typical detectors are such that the gain will not fluctuate wildly at short timescales, and so the extent, or to the extent that this is a wrong assumption, the varying of the gain will be sucked up into the signal or the noise. But it turns out that this is a very good approximation. And for Planck, as I said, what slowly means is a matter of definition. What we did in Planck, when we reanalyzed the beyond Planck data, was to assume that the gain was constant over a period of an hour. Because Planck measured these great circles on the sky for about an hour before it readjusted and scanned another circle. And each of these scans took about an hour each. So we assumed that the gain could not vary on scales shorter than an hour. And this helps break the degeneracy here, because the noise is typically fluctuating at a scale that is comparable to the sampling rate of the instrument, which is obviously a lot faster than an hour. Further, in order to try to find other ways to lift this degeneracy, we can have a look at what kind of sources we are looking at in order to do our gain calibration. As I mentioned, if we were on Earth, we could have a flashlight shine into our detector, and since we would know the intensity of this, we would also know the gain of the detector if the gain was constant in time. But obviously it is not. So the question then is, are there any sources, any mysterious question mark sources, which we can point our detector towards, which will help us lift this degeneracy? What kind of properties must that source have in that case? So one of the ways in which this mystery source could help us lift this degeneracy would be for whenever the gain varied, we would see something in the data that looked different from the noise. And one of the ways in which that could happen would be if, for example, if this is the typical time stream of white noise and observations, and then all of a sudden we see something like this in the data. This doesn't look like a normal noise jump unless we know something specific about the noise. So if we see this and we know that the signal is basically the same, then this must be due to a change in the gain. And for this to happen, I mean, the signature here is basically that the fluctuation is a lot bigger than a typical noise fluctuation. So if we have a short little list here of what kind of properties our mystery source should be, the first one is that it should be a strong emitter. Something that is so strong that when we look at the data as the G times S plus N, and we have a delta G times S, then we see this change in data as something big, and that must mean, unless this fluctuation is big in itself, then this signal must be very strong. So that's the first property that we want from a source. The second way in which a source could help us lift this degeneracy would be if the source had a signature, emission signature that we knew perfectly well, because then we could look for that signature also in the data, and presumably it would be very hard for the noise to replicate this perfectly. So we would know that when our data varied, it would be because the signal varied, and thus we could adjust the gain so that it matches up with that variation. So for example, if we had a source that behaved like this, and we saw that exact pattern in the data, of course with noise fluctuations on top, this would still be a very strong signal compared to the noise on top. And so we could use this information here to disentangle this and to know exactly which part of this is signal and which therefore must be signal times gain, and thus we could solve for the gain. So the second property of the source should be that it is well known. It has a well-known emission signature. So those are the three things that I wanted to mention that we do in order to perform gain estimation more effectively, to basically try to lift the degeneracy between the gain and the noise. The first one has to do with restricting G so that we assume it to only vary on slow timescales, which is a pretty accurate assumption. And then a couple of things we should be looking for in our sources. And we will be talking about what kind of sources we are using that have these properties. I talked a little bit about the characteristics that we want from our calibration sources when we want to estimate the gain, so that it can be easily disentangled from the noise. The two characteristics I mentioned were, first of all, that the calibration source should be a strong emitter. The signal itself should be strong. And the second one was that it should be something that we know very well, that we have a very good idea of just how the signal emits over time, so that we can match this up with the actual data. It turns out that what we call the dipoles exhibit these two characteristics. So let's talk a little bit about those. From physics, you may remember that if there is a source that is emitting waves of some kind, where you have something that registers these waves that is traveling, for example, towards the source, this detector will see these waves as having a shorter wavelength than originally. And likewise, if it's traveling in the opposite direction, the waves will have a longer wavelength. This is what's called a Doppler shift, or a Doppler effect, I guess. In the CMB context, this means that if you have a detector that is traveling towards the source, that source will look a bit hotter or with a higher intensity. And if it's traveling from it, it will look colder or with lower intensity. In the CMB context, we have Earth with an accompanying detector, for example, Planck or WMAP, and which is observing the CMB. And we know that the CMB is a source of electromagnetic radiation, but it's a source that is basically emitting from all sides. Radiation is coming. This is an S for source, and there's basically waves coming towards us from all around. And if Earth has a speed relative to this the rest frame of the CMB source, then we will expect it to exhibit a Doppler shift. And that's exactly what happens. Earth does have a velocity, and so in this direction, when the instrument happens to point in this direction, the CMB will look hotter, and likewise when the detector is pointing in this direction, the CMB will look colder. Cold and hot. So this movement and the fact that the detector is moving relative to the CMB rest frame will induce what we call a dipole. So if we draw a map of the sky, the CMB sky, we will see this kind of yin-yang pattern where you have one side which is hot and another which is cold. And this is the center of this area is where it's the direction in which Earth is moving relative to the CMB rest frame. And likewise, this is where it's coming from, or where it's, the direction is traveling away from, basically. This movement induces a CMB dipole. This is a dipolar pattern. This is why it's called that. There are two sources of movement that induces a dipole. Both of them make the Earth move relative to the rest frame, but they come from two different reasons, so to speak. So the first is the fact that the Sun and Earth and the whole solar system is moving relative to the rest frame, which is both due to the movement of the Milky Way in relative to this CMB rest frame, and also the fact that the solar system is moving inside of the Milky Way. So this movement induces a dipole called the solar dipole. And then you have the hopefully well-known fact that Earth is traveling around the sun. And this movement around the sun makes the Earth have slightly varying velocities relative to the CMB rest frame at all times. So after a year, it's back to the original, but after half a year, the dipole induced by this movement is completely opposite to what it was here. This dipole is called the orbital dipole. So let's have a look at the characteristics of these two dipoles and how they can be used for calibration. So in order to have a look at the characteristics of these two dipoles, let's imagine that we have a detector, and as always I'm just going to use Planck, which was scanning the sky in these great circles. When you scan the sky like that, if we draw the CMB map, you scan along certain certain circles in this way, and no matter how you do that, you will scan the dipoles, obviously. So let me try to draw just what the dipole contribution to the total signal that the detector would measure on these great circles. With the solar dipole, if we say that looks something like this as a function of time, so this is just within one of these circles, then you would have the orbital dipole, which would have a slightly different period, but also be a lot weaker on average. And the reason for this is that the speed at which the sun moves relative to the CMB is a lot greater than the speed at which Earth is moving around the sun. So if we recall back to the properties that we want our calibration sources to have, it seems like the solar dipole at least exhibits one of these, which is that it's a strong emitter. The second thing we wanted was to have a source that had a very well-known known emission spectrum. And although the solar dipole seems to be very well behaved, and it seems like this should be a very regular source that we can calibrate on, the fact is that we don't know exactly how fast the sun is moving through the universe, or through relative to the CMB rest frame. And also we don't know exactly the direction here. So we know roughly where the sun is moving, but there's some uncertainty here. So unfortunately, the solar dipole doesn't exhibit this other quality that we would like the calibrators to have, which is that it should be well known. The orbital dipole, although as you can see, and it's more exaggerated than what I've drawn here, the orbital dipole does not have this quality of being a very strong emitter. So unfortunately, it doesn't satisfy that. But on the other hand, we know perfectly well how Earth moves around the sun. That has been measured to a very high degree. So well-known spectrum is something that we definitely know about the orbital dipole. So these dipoles seem to exhibit each of the two qualities that we would like our perfect calibrator to have, but not simultaneously. So which of these dipoles should we use for calibration? The orbital dipole, if the gain was a constant, then the orbital dipole, although it's weak, and so it's dominated by a lot of noise and effects like the galaxy spiking up every now and then because the observation is crossing the galactic plane, which lies in the middle here. Although all of these things dominate over the orbital dipole, if we integrate this over a long enough time, it would still be the fact that we know exactly how it behaves would still allow us to estimate the gain pretty well. If the gain was just constant throughout the whole mission, it would provide a statistically strong estimator for the gain. The solar dipole, on the other hand, dominates over the noise and these galactic spikes and so on. So for short-term gain estimations, the solar dipole is clearly to be preferred. The orbital dipole would be too weak for this. And this motivates a kind of a splitting of the gain into a constant part, which we assume to be constant throughout the whole mission, and then we add a fluctuation part on top of that. And the idea then is to try to set things up in such a way as to be able to calibrate the constant part of the gain on the orbital dipole, and then have the fluctuations be calibrated on the solar dipole. So that would give us, in a way, the best of two worlds. We would have, we would be able to use the orbital dipole to estimate a gain factor that is constant for the mission, which kind of sets the baseline for the gain, so that it's not free to just fluctuate and be anything. This is the baseline around which it should vary. And then we have the fluctuations, which we estimate using the solar dipole on top of that. And we shall see later how this is accomplished. So let's now look at what gain estimation looks like in the context of Gibbs sampling. You probably know by now that in the Bayesian framework that we work in, the goal is to map out the posterior distribution of all our parameters, like the total CMB signal, the dust signal, all the other signals, power spectra, the gain, correlated noise, and other parameters given the data. And with the Gibbs sampling framework, what we do in order to try to map out this posterior distribution is to sample each of these conditionally on all the others, like this. And we do this for all the parameters, and then of course then including the gain. There is a thing to note here, which is that as we have seen, the gain and the correlated noise are degenerate with each other. So let's have a look at this simple data model again that we have looked at before, where now I write the noise as the sum of the correlated noise and the white noise. And the point now is that even with all our tricks for example, considering only slowly varying gains using the dipoles for calibration and so on, there is still a degeneracy between the gain and the correlated noise. And that degeneracy comes about because if we change the gain factor, we can, in many cases, select a correlated noise factor that counteracts the product of the gain times the total signal. The correlated noise acts in many ways like a kind of garbage can, which collects all of the excess unmodeled signal that we're looking for. And so that happens especially with the gain and the correlated noise duo. So in the context of Gibbs sampling, if we assume that if we only are interested in two parameters, but that those parameters are very correlated with each other, so that their distribution is very thin and very diagonal in the space that those two parameters are mapping out. We can assume that if we start with this value for one of the parameters, well, this value, then when we're sampling this parameter, the y, let's call them just y and x, we're only sampling from this very narrow range right here, so it will fall somewhere here. And then when we are sampling x, we can only sample within this very narrow range, so maybe here. And again, poor drawing skills, but the point is we will move very slowly through the whole distribution when we do Gibbs sampling with two highly correlated parameters. One way of counteracting this slow exploration of the correlated parameter space when we sample the conditional distributions after each other like this is to instead consider this distribution, the joint distribution of x and y. And this is just considering this whole thing and sampling directly from that instead of slicing it in narrow subdimensional spaces. But the astute video watcher might have an objection here, which is that, well, the reason we went into Gibbs sampling in the first place is that these are distributions that we can sample from and that we know, whereas this thing we don't really know how to sample from that. And that is generally true. So what we can do is to use a trick from probability theory, where we say that the joint distribution of two variables is equal to the marginal distribution of the first variable multiplied by the conditional, or the second variable, probability distribution of the second variable conditional on the first one. So this, if we are able to find these two distributions, we can sample jointly from the degenerate distribution. And the way that works in practice is that we have this thing, and now instead of, now we can for the x variable, which is not conditional on y anymore, we can basically sample from the whole line here. So when we sample from y, we're still constrained to this narrow thing right here, but x is unconstrained and we can jump around as we please. So we're not saddled with that problem degeneracies anymore. Turning this back into our original problem, this means that instead of sampling G given n core and everything, what we want to do is sample P of G and then sample P of n core given G and everything else. Now note that this thing is exactly the same as a normal Gibbs step for the correlated noise. So this step is completely unchanged. This step, however, means that we don't consider the correlated noise as a known quantity. Instead, we have to marginalize over it. And we will see how that plays out in practice once we consider the actual sampling equations that we will use. When we're doing this step, we have to be mindful that what it really means is that we are doing this thing jointly. I mean, we've used this identity right here to separate them into this, but that means that this is the step in the Gibbs sampling process that we're actually performing, which means that when we're sampling the gain like this, we need to sample the correlated noise right after. We cannot have any of the other variables in this area in between. Basically, so right after we sample the gain, we need to sample the correlated noise. So our current task is to try to figure out a way in which we can draw a sample from the conditional distribution of G given all of the other quantities. I'm just gonna dot them here and including the data. If we put our Bayesian hats on for a second and just look at this as a function of G and the data, and we see that, oh sorry, not an equal sign here, but we see that this, what we have here is the posterior distribution of G, which we know from Bayes' theorem is proportional to P of D given G and everything else, which we can see as the likelihood function of G. So we're essentially drawing a sample from this thing. And in order to do that, let's start with a very simple case where we consider just one pointing period during which the gain is constant. So basically we have data for however long this pointing period is. That's chosen by us, but for Planck, for example, we set that to be an hour. So over the course of an hour, we get data that looks something like this. That's instrument scans the whole sky or encircles on the sky for a while. And our task then is to use the data as a function of time to estimate a single scalar G. So G in this case is a scalar, and our data model is that for every time t, we have a data sample that is, again, we're using a simple model without a lot of beams and side lobes and so on. We're saying that that's equal to this constant gain factor times the actual true signal at any time t, because the detector is pointing at different places for every t, and so the signal will vary depending on which time it is. And then we also add this have a noise term, which also will vary from at every point in time. This is a least squares situation, which well, I'm not going to go into the theory here, but if you have taken some Bayesian statistics, the likelihood function of this thing is a normal, which is given by the mode of or the best fit solution to this equation, which is incidentally given by oh sorry, not S but D. So if we consider S and D to be vectors, divided by S squared. So this is the normal, the solution to the normal equation. So basically it's a normal with this sorry, D. with this mode, and a variance that is given by the variance of G, which also from the theory behind this equation is given by s squared to the minus 1. So that's that is our variance. So that means that we can draw a sample by, if we call our sample G hat, it's given by S times D divided by S squared. And then we add, so this ensures that we get the correct mean. You should have seen this in a previous lecture. This is how we draw from a univariate normal. And then we add the square root of the variance, so 1 over s squared multiplied by this eta, which is then a random number drawn from a normal distribution with unity variance, and this ensures that we get the correct mean and correct variance with our samples. All of this was assuming that this noise term was actually drawn from a normal distribution with unity variance. If we instead assume that our noise comes from a more sophisticated noise model, which has some kind of covariance matrix, confusingly I have to use the same letter, but hopefully by the context it should be clear. If we look at our equation, our data equation, we still have dt equals g times st, t plus nt. And if we now multiply this by the square root of this matrix, of the inverse of this matrix, this term, since this factor had a variance of nt equals n, then that means that this term ends up having a variance of 1. So that's exactly the situation we had in our simpler example, which means that the mode must just be given by S and G multiplied by these factors. So in a more realistic situation, the sample G this means we have to replace our signal with signal times square root of n to the minus 1, and the same with the data. So what that ends up being is actually this equation right here. And squared. So with a noise covariance matrix, then this ends up being the correct equation for sampling a single scalar value of the gain for a single pointing period. And this holds no matter whether our noise is white noise or correlated noise or whatever. So this is our sampling solution for a single gain factor, and this holds no matter what kind of covariance matrix this is. So that means that in the case where the noise is pure white noise, which means that the covariance matrix is diagonal in pixel space, sorry, in time domain. And this, in that case, this sampling becomes quite easy. All we have to do is multiply each of the elements of S with the diagonal elements of N, and so on. So in that case, all this reduces to simple array operations. But in the case where the noise is a combination of white noise and correlated noise, which is what it is when, so calling back to what we had before, I said that this is a sample from the posterior distribution of G, but it's given everything else. And if everything else included the correlated noise, then that would mean that our data model, or what was on the left-hand side here, was really the actual data minus the correlated noise. That's the way to account for, because in this scenario we know exactly what the correlated noise is, and so we don't want to include that when estimating G, and so what's left on the right hand side is just the white noise. But when we marginalize over the correlated noise, which we have to do if we want to sample G and the correlated noise jointly, then we don't know what the correlated noise is, and that amounts to actually having our data be given by the signal plus white noise and then plus this correlated noise term. And that means that our covariance matrix is given by a white noise covariance matrix, like this one, and a correlated noise covariance matrix. And this covariance matrix is not as well behaved as this. It has a lot of elements, or non-diagonal elements, and that means that the matrix operations here become a lot more expensive. And that's the cost of marginalizing over the correlated noise, is that we have to take into account more expensive noise covariance matrix. So we have now seen how we can draw a sample of a single gain factor for a single PID, whatever we define our PIDs to be. In Planck, as I said, we define those to be about an hour of observation time, after which the instrument readjusted. And in principle, we could now just extend this procedure to cover the whole mission, and estimate the gain for each PID consecutively. So for Planck, for example, that would mean estimating about 45,000 gain factors by just placing the data after each other and estimating a single gain factor per PID. But there are a couple of things that I have glossed over so far, which we need to start taking into account at this point. And the first one has to do with the fact that we want to be able to calibrate our gain as much as possible on the signals that are very well known. So I wrote down this data model, very simple one, which we'll keep using, but the problem with this signal right here, even though we are part of a Gibbs loop and the signal is in principle, it's the CMB plus the dust and so on. In principle, these are perfectly known at this point because we are in a Gibbs loop, and that's kind of how we operate. But the problem is that even though this might be true, theoretically, there might be systematic effects that we have not accounted for in our model, which affect these signal components in such a way as to bias them somehow. And that means that these estimates every time we get into the gain part of the Gibbs sampling process, these might contain some systematic effects which will affect the gain estimation. So as we mentioned, we would like to have a calibration source which is perfectly known, and what in order to avoid these systematic effects. And what I mentioned back then was that the dipole, which is called the orbital dipole, is one such factor which is perfectly known. And the problem with the orbital dipole is that it is very weak. And the problem with that is that we have a lot of, so if we have this underlying orbital dipole, we first of all have a lot of noise, and then we have stuff like the galaxy, which spikes up every now and then, and other signals that add to this to the noise here. So for short-term gain estimation, the orbital dipole will give very uncertain estimates. But if the case was that we only had a single gain factor to estimate for the whole mission, then this underlying signal would go over such a long time, 4 years in the case of Planck, for example, that it would actually provide a pretty robust statistical estimate of the gain. And so that motivates us into maybe we can write the gain as a short-term part, this gamma right here, and then a long-term part. And the strategy then would be to estimate this parameter using the orbital dipole, and then the short term using, for example, the much stronger solar dipole, where the galaxy spikes and so on are a lot less significant, and which is dominated a lot less by the noise. And that means that essentially what we've done now is that we have replaced this single parameter with two parameters, G naught and gamma. And so each of these has to kind of go into their own. When we're doing this, instead we're doing P of G 0 given gamma delta and everything else, of course, and then sampling this given the. So we call this the absolute calibration, and then we can call this the relative calibration. At this point, we have to clean up our notation a little bit. So we have now split our gain into this G naught plus gamma. What we need to keep in mind is that all of these now are things that we want to estimate for several PIDs. So these are not scalars anymore. And we will use, instead of, I've used T as a time index, and I will use P as another time index, but which signifies the PID index, basically. So since the gain are allowed to vary only on the scales of separate PIDs, we will use P as the subscript for these. G naught is going to be constant for all PIDs, so we don't add a subscript to that. And what we have to do now in order for this whole splitting to make sense is that we have to impose a constraint on gamma, which is that it needs, if we sum over all of the p's, this needs to sum up to 0. Otherwise, this is no longer the absolute calibration, and if this is not 0, then it's essentially allowed to steal power basically from this term into gamma. But with this constraint, all of what can be put into the average will remain in this absolute calibration term. The next thing that we need to keep in mind is that all of our discussion so far has basically been about a single detector. When I wrote this this equation earlier, this was all in the context of one detector. But for a typical CMB experiment, our instrument, like Planck or any other instrument, will typically have more than one detector. So that means that we have the task of estimating the gain not only for each PID, but also for each detector, which I'm going to index with I. So I is going to be the detector index. Still, we are going to assume that all of detectors have the same absolute calibration, G0. But now we have to make this gamma also include an I term. And that means we also have to ensure that when we sum over, or that this sum includes the detector index as well. Turns out that this becomes a lot more easier to enforce if we do another split. That is to say, we let our gamma become two new terms, which we call capital delta G and regular delta G. And I will explain this. I will explain this notation. So what we're saying here is that the gamma is split into, once again, a semi-absolute calibration term, which is not allowed to vary between PIDs, but can vary between detectors. So if we imagine that we have 3 detectors here, and we plot G, we all start at the same G0, basically. This is where this term. And then for detector 1, maybe we add, so if this is G0, we add this thing here, which is then delta G1. And maybe for the second detector, we have this thing be delta G2, and so on. So delta G3. And again, we now enforce this this constraint right here. Or we have to make sure that when we sample, this thing is enforced. And then this term is what actually encodes the PID to PID variations. So that would be if this is the PID index or axis, the actual total gain would look something like this. That's when we add all 3 of them together. But we have to make sure that for each I or for each detector, the sum over all PIDs is 0. So in essence, we have now replaced, or we are going from this equation, or from this from wanting to sample from this distribution to sampling from, or going to a kind of a sub Gibbs loop. So we're essentially splitting this into three separate sampling operations, which will come right after each other, and that is given by G naught given delta G I and delta G P I and CMB and everything, and same with the two others. So sampling delta GI given G naught delta G P I and so on, and for this one. So our task going forward now will be to figure out how we can sample from each of these three equations. So we will sample the absolute calibration given the two others, for example, and similarly with the two others. So let's have a look at how that can be done. So then now the time has come to figure out how we can draw a sample from the conditional distribution of the absolute gain. G naught given the other gain quantities and everything else, including the data. If we take some inspiration from our previous foray into this, we had the data equation that was given by as data T for a given detector I is equal to the gain for that PID times detector I times the signal at time t detector I plus the noise of time t for detector I. And we would like now to massage this, or to figure out a way to create some kind of quantity that, instead of, because what we have here is the total signal, which is the SCMB plus S dust plus S orbital, etc. What we want is to estimate G naught using only S orbital. So we want to replace this by G naught, and we want to replace this by the orbital dipole. So in order to do that, let's first subtract this term. So we subtract, oh, sorry, it's a bit big for a subscript. And then we add back in G naught times S orbital at time t for detector I. And this will depend on the detector, because at the given time, not all detectors will be pointing at the exact same location in the sky. So we need to include that in both for the total signal and for the orbital dipole. And so if you write out then the this factor G here, because we're doing something that is a bit sneaky, we see that we know that G, the gain is the sum of the absolute calibration and capital delta G and delta G P I. And so this is now our left-hand side, and then, oh, sorry. This is not the total signal. This is the orbital dipole. So what is left on the right-hand side is then just G naught plus or times S orb plus the noise. But as you can see, we in our left-hand side we already also have this G naught term. So this is not only sneaky, it seems almost a bit wrong. So what we do is basically to use the previous sample of G naught to form this residual right here. So our residual RTY is what we call this whole thing, and that is given by G naught times S orb Ty plus N Ty. So if we take our data and subtract these quantities and add this quantity with our with these two being our previous sample of G naught, and this implicitly then being the sample we want to draw, then we form this. So we are trading a bit of rigor here for the ability to use the orbital dipole to estimate G naught. So our residual that we are working with is supposed to be equal to this quantity right here, keeping in mind that that G naught is going to be constant for all detectors and all times, so we don't need any indices for this. Now, in order to see how to solve this, let's start with the case of one detector. So I equals 1, we can just drop the I essentially. In that case, we have RT equals G naught times S orb plus NT. And if we draw this here, what we had earlier, since we're now working with only the orbital dipole here, what we're supposed to have is a very weakly changing curve. And earlier I drew this I said that this was an hour. So basically what we're doing now is we are now using the whole mission for this. This factor is supposed to be valid for the whole mission. So we can essentially continue this for all of the PIDs and just append them after each other. So S, or this orbital vector is basically, if we imagine that we have the first one, the first samples of the orbital until the end of the PID, and 1, so that's the first PID, and then we just keep stacking them onto each other like this. And we do that for all the PIDs, so this becomes a very, very long vector. And we know from earlier, there's no difference between this equation and what we had when we just looked at a single PID for a single detector. And so we know that a sample for this, for G naught, is given by S orb, and inverse, not the data, but the residual, and then S orb. So this is transposed orb, transposed, and inverse S orb. And then 1 over square root of S orb transposed as my 1 S orb times eta. This is how we drew a sample for with this model right here. And what we need to have a look at now, which is the non-trivial part of this, is what does the noise covariance matrix look like here? Because we know in general that this n is equal to the white noise covariance matrix plus the correlated noise covariance matrix. But that was in the case of we had a non-diagonal matrix. But this is in the case of a single PID. So let us call that NP. So that's for one PID, for a given PID index P, we have a non-diagonal matrix. But we, in Planck and probably other instruments, what we have done is to assume that there are no correlations between PIDs in terms of noise. So even though we have correlated noise matrix, it's not correlated across PIDs. And so if we write down the total covariance matrix, we can write it up as blocks of, so we, if all the rows here now are PIDs basically, so P, we basically get a matrix that is diagonal in these blocks, but where each of these blocks in itself is one of these matrices right here. So between PIDs, there are no correlations, but within the PID we have this correlated matrices. So that means that if we assumed correlations between PIDs as well, these would be non-diagonal, and this would be quite hard to calculate, because you would have 44,000 PIDs in a row here, multiplied by how many samples are per PID, which amounts to quite a lot, and these matrix operations would become quite unyieldy. But as it is, we can now essentially separate this complete equation with all of the timelines into kind of a sum over PIDs, where each of these signals per PID is multiplied by the relevant covariance matrix for that PID. So that simplifies things a bit. And this is for the single detector case. And now let's have a look at what happens when we add multiple detectors. When we extend our sampling to include all the detectors of an instrument, we are then again looking at this residual Ey, which is equal to G0 times plus this. And again, just as when we extended from a single PID to all the PIDs, there is nothing in principle that separates a data stream from one detector with the data stream from another. Both of these are equally valid estimates of or contributors to the estimate of G0. So in the same spirit as when we just added together each PID, we can do the same thing with each detector, and just say that the total signal is given by the total signal from detector 1 and and from detector 2, and so on, concatenated like this. And in the same way, we can say that our total covariance matrix, now we got to keep our head straight, is given by blocks of these sub-covariance matrices that we looked at earlier. Where we had the diagonal elements, diagonal covariance matrix blocks for each PID, and we can set these per detector into similar blocks. So this whole block now corresponds to detector 1, and this is detector 2, and everything else is 0, because we assume that there are no noise correlations between detectors. And that means that our solution, again, for a sample of G0, is just going to be everything here is in principle diagonal down to the PID covariance matrices, and so we can just multiply the sub elements of a detector 1 signal with the covariance matrix from detector 1, and so on. So what that ends up being is a sum over I and a sum over the PIDs of S orb for a given I and a given P multiplied by an inverse I P S orb. Residual for I P. So this is transposed divided by S orb IP and inverse IP, and again we have a sum here over detectors and PIDs, and we have the S orb PY, and again we have to add, of course, the fluctuation term, which becomes this. So this is the final prescription for estimating the absolute calibration term. This is a valid sample from the distribution, the conditional distribution that we have looked at. So now we can move on to the two other gain factors. So let us now turn our attention towards the detector-specific gains, the capital delta GI, and let me gather those up into a vector where the first detector-specific gain, and then for detector 2, detector 3, and so on. And so our goal is to figure out how to draw a sample from this conditional distribution right here. I'm still gonna put a time index on these, but all the detector specific things are put in a vector. And what I said earlier was that we would like to estimate these factors using the orbital, nor the solar dipole. And I also said that the solar dipole is strong enough that it dominates all of the other signals. So that means that we can just use the total signal when we want to estimate these. And going back to our data model, we then have that time, or the data at any given time for any given detector is given by it's given by the gain times the total signal plus the noise. So right now we're good with this. This is what we want to calibrate on. All we need to do is to take away the gain factors that are part of this sum, which are supposed to be the ones that we know at this point in the Gibbs loop. So we know that Gi is given by G0 plus delta Gi plus delta Pi, like this. And that means that if we make if we create a residual RTI, which we define as being equal to the data minus G0 plus delta G Pi times the total signal, then that is supposed to be equal to delta Gi times S tot plus NTI. So that means that we're back to the situation that we've seen a couple of times now, where we have kind of a data factor on the left hand side that is equal to the parameter that we want to estimate times the signal that we know plus an unknown noise term, which is modeled by a covariance matrix. So this we know how to solve. And if this is this was the whole story, this could be written as the factor of G1 given everything, G2 given everything, and so on. These would be independent. There would be no correlations or constraints that made these dependent on each other. But there is one thing that we need to keep in mind, which is that we want to make sure that the sum over all detectors of these gain factors is supposed to be 0. So how can we enforce that? One way is to proceed like this. We draw a sample from each of these independently, like we know how to do now when we've seen this equation several times. And then after the fact, we just take the mean of our samples. So we sum up so I put a hat here now, sum up the GIs is equal to something, mean of G, and then we just subtract this value from all of the factors. That would enforce this. But the problem with that would be that it would enforce it in a way that would give equal weight to all of so none of the estimates of GI would have a higher or lower weight in this sum. And what we would like to do is to have the more well-defined or well-estimated GIs have higher weight than the more uncertain ones. So it would be better if we could include this or enforce this as part of the whole sampling process. So thinking back to when we had a scalar gain factor that we looked at with a single PID or observations from a single PID, the way that we found the mean value of the sample that we wanted to use was to look at the mode of the likelihood function. We didn't do this in detail, but the least squares approach is basically doing that. And so that means that we minimize this function. And what we want to do right now is to do the same thing. We want to minimize the likelihood function of these guys, but we want to do that subject to this constraint. And one way of minimizing a function, let's call it a function f of x, subject to some kind of constraint. Let us call that constraint h of x equals 0. So let us assume that our constraint can be formulated in this way. Then we have the so-called method of Lagrangian multipliers, where we form a Lagrangian function, which is then given by the f of x plus some lambda, which is just a dummy variable, times this constraint function. And the method of Lagrangian multipliers says basically that in order to minimize your function f of x subject to h of x, oh, let me put this here, you need to take the partial derivatives of your Lagrangian with respect to x1 and set that equal to 0, x2, and so on. And then finally, you also have to take the partial derivative with respect to lambda and set that equal to 0. And when you do that, you will minimize f of x subject to the constraint expressed by h of x. So in our case, of course, the constraint will be this. So let's have a look at what this looks like in our case. So now we need to figure out which function we want to minimize, the f of x in the Lagrangian formulation, where in our case x is the delta g vector. And what we did earlier was to look at the likelihood function and minimize that. We didn't explicitly derive it, but that's how we arrived at how to draw a sample from the posterior of G. So naturally, what we want to minimize is this likelihood function of delta G, which is equal to the probability of observing some data given this. And the data in our case is given by the residual that we formed earlier. Now this includes both all the detector residuals and every point in time. And in order to explore what this looks like, we have said before, or when we touched upon this before, I briefly mentioned that this is a Gaussian, but I was a Gaussian in delta G, or in the gain. Now we want to look at the function itself, just how what it looks like functionally. So let's write down. Let's keep it as a vector actually in time, but for a given detector. We don't assume any data correlations between the detectors, so we can write down these equations detector by detector. It is only when we introduce this summing that we get correlations between the various detectors. But in any case, we have this relation here, and then so this is the entire time stream put in a vector for a given detector. And if we now then subtract this part, we end up with this term on the right hand side, which we know is a normal given by some covariance matrix, which means that we can write the probability of observing R given delta G is given by or is proportional to the exponential function of minus 1/2, and then we have to then we put this guy in here. Transpose it, and then multiplied by this, and another factor here. And this is for a single detector I. But what we need to keep in mind is that this equation is true for all the detectors, but since they are independent, we can write the total likelihood as a product over I. So again, it's proportional to this, which means that when we multiply several exponentials together, this becomes a sum over I inside of the exponential. So this is our likelihood function, L of delta G, and we want to use, this is what we want to minimize, but we are free to minimize the log of this because they have the same mode. So the point that minimizes this function will be the same point that minimizes the log. So our Lagrangian is going to be the log of this. And the reason we do that is because it's a lot easier to differentiate the log than it is to differentiate this function itself. And then we add, again, this constraint. Oh, sorry. Not over G, but over I, delta GI. So our task was to take the partial derivative of this with respect to delta GI and set it to 0 for all i's, and with respect to lambda. Now this one is pretty easy because the likelihood function doesn't depend on lambda at all. So this, of course, just gives us the constraint back. This is one of our equations. And so our next task is to differentiate the Lagrangian with respect to delta GI. So let's write down the log of the likelihood that we're working with. So we can just forget about the minus 1/2. That doesn't shift the mode. And what we're left with is a sum over I. And then we don't have S, but we have the residual. And for the detector I minus delta GI times S tot multiplied by the inverse covariance matrix, and then this factor. So this is transposed factor one more time. And then we can form our Lagrangian, which is supposed to be this function plus lambda times the constraint. So again, it is log likelihood plus lambda times this thing. And then taking the partial derivative of the Lagrangian with respect to our variables, which are the delta GIs. This gives a -2 times one of these factors. And then the matrix multiplied by S tot. And then differentiating this with respect to so in both cases, the sum over I just leaves the the element that corresponds to the I that we're differentiating with respect to. And so we get 1 lambda here. And similarly, if we take the derivative with respect to lambda, this whole thing, the log does not depend on lambda at all. So what we're left with is just the constraint. And both of these are supposed to be equal to 0. So this we already knew. And cleaning up this equation a little, we get delta gi si tot transposed. Yeah, sorry, this is supposed to be transposed. Times s tot plus lambda halves equals, and we get this r and this makes sense, because if we let lambda be equal to 0 here, we end up with the exact same equation that we had before, where we had delta gi equal to the residual times the signal divided by the signal squared. So this is our new equation for the mode of our samples, and this becomes a system of equations now, where this is kind of the common factor. But the mode is not all we needed to draw a sample. So if we wanted a hat sample of delta gi, we also needed to add the fluctuation term. And just we're gonna have to stay with or keep this on this part of the equation on the left-hand side, because it's a bit unruly otherwise. So this, so this is what we're having, and then we have to add an eta, and then we have to add the fluctuation term, which we remember before we had eta times 1 over s transpose and inverse s. And in order to get that with this factor on the left-hand side, we have to have this in the numerator instead. So s tot and sorry. Like this. So this is our sampling equation for delta gi, and we also have to include this equation in our system of equations. So solving this system of equations for delta gi will give us a sample from this distribution, and that sample will have taken this constraint into account. So that is built in when we get this additional term. So that's all there is to sampling the detector-specific gains, and then I will move on to the third part of the gain factor, the time variable gain. We now have a prescription for drawing samples of absolute gain and the detector-specific gains. And finally, we want to figure out how we can draw samples of this conditional distribution. I'm just not using vectors right now, just a notation to symbolize what we're talking about. And these are the fluctuations of the gain that are allowed to vary both between detectors and for each PID. We want to estimate this in the same way as with the detector-specific gains. We want to use the total signal or the solar dipole for estimating it for the same reasons. So if we write down our data model again, we have and using the same trick or forming a residual that has only the temporal fluctuations. We define that as being the data minus the sum of the absolute calibration and the detector-specific calibration multiplied by the total signal. And on the right-hand side, what is left is then this part. And if we have a look at this, and we keep in mind that each of these multiply a bunch of signals that belong to the same PID. So for a given P, we have this signal that lasts for about an hour, and this is meant to be used to estimate each of these, and that's a bunch of T's basically. And we've encountered this situation before. When we assume just a single scalar gain factor and use that to estimate this. So we know in that situation exactly how to draw a sample. And in principle, as far as we know right now, there's nothing really keeping us from doing the same thing, because we don't assume any noise correlations between the PIDs, and for the time being, we also don't assume any correlations between the PIDs when it comes to the gain factors themselves. So from PID to PID, right now we allow the gain to vary completely freely. But we shall see in a little while that it is a good thing to assume that they will be correlated in some way. And so what we need to do here is find some notation that makes it clear that we're considering not only a single PID, but the totality of all PIDs for a given detector. So for that detector, we have the whole signal, S1, S2, all the way to the end. But only the first part of this is the first PID, and that's supposed to be multiplied by DG1. And then the next part is supposed to be multiplied by DG2, and so on. In order to make that notation more clear, let us now consider this as a vector, which has this n samp, which is equal to the size of this, basically all of the samples of the mission for a given detector. And that is given by, we'll introduce a matrix Ti and multiply that by a vector of temporal fluctuations of the gain, and then we add the vector of the noise. So this is as well an n-samp sized vector, whereas this thing, it needs to be, of course, npid. So that's the number of PIDs, which is not the same as the number of samples, because each PID contains an hour worth of samples for Planck at least. That must mean that this matrix is an n-samp times n-PID matrix. And we can arrange that in such a way as to kind of fulfill what we needed to do. Writing that down, we can arrange our signal in such a way that the first column here corresponds to the first PID, because this is an n-PID sized matrix in that direction and n-samps in that direction. And if we let the first the samples corresponding to the first PID, so end first PID, and then the rest of these is set equal to 0. And we do that similarly for the others. So for the second column, we set all of the samples equal to 0, except for the samples that that belong to the second PID. So n plus 1 and so on. And then the rest is 0. And we keep doing that and multiplying that by this matrix, or this vector, which is dg1, dg2, delta g3, and so on. Delta g and PID. And so what we end up with is then an n-size or n-samp sized vector, which the first element of that vector is just s1 times delta g1 plus a bunch of zeros. So delta g1 times s1, delta g2, or delta g1 s2, and so on until we have reached the end of the first PID. And then further down we will have delta g2 times sn plus 1 and so on. So this this equation is basically what we will be working with to draw a sample now. If you recall back to the discussion about when we sampled delta GI, I said that we couldn't just consider each of these in isolation and then just draw samples, independent samples from delta GI, because they were connected through the fact that we needed this to be true. So that made us that's forced us to basically draw from the total vector the joint distribution instead. Ideally, we would like that to be true here as well. We would, because we still need to take into account the fact that we need, when we sum over the detectors and the PIDs, we need this to be 0. And we could proceed in somewhat of the same way as we did with the capital delta, and use the Lagrange multiplier to enforce this in this with this equation. The trouble is that there are so many equations to be solved in that case that it would be completely intractable. So unfortunately, what we're going to have to do is fall back on what I mentioned briefly, which is just to sample this without this constraint taken into account, and then after the fact calculate the mean value of the samples and subtract that value from all of them, and that will enforce this. But that will be suboptimal, because then each of the PIDs will have equal weight in calculating this mean, whereas it should ideally be more weighted by the noise and so on. But that means that we are free now to consider only this equation without thinking about the correlations between detectors. And this equation you might have covered now in one of the other courses. This is a multivariate Gaussian draw, basically, where we have this template matrix that projects this vector into the space of the data. And the solution is quite straightforward. If we remember from the previous, what we have arrived at previously, we get something that looks like this, where we have, instead of the signal now, we have these template matrices which contain the signal, obviously, multiplied by delta gi vector equals, and then we have the template matrix again, times the residual here, and then plus a fluctuation term, which again must be given by the square root of the like this. So this is, in all simplicity, what we end up with for the temporal gain fluctuations. These are all detector specific, and so we're free to do this for each detector, and then once we have drawn the samples, we enforce this this constraint by calculating the average and subtracting that from our samples. In one sense, we're now done. We have found ways to sample conditionally, sample from the conditional distributions of these three guys. And the total gain then is just a sub of them. So we have that. But there is one thing left to say and to do, and that we can see when we plot the temporal fluctuations as a function of PID. We will typically see it vary around 0 because we're enforcing the sum of them to be 0. And what we have here is that that the fluctuations are varying much faster than what is physical. Typically the gain is variances are smoother than this. And this happens because for each of these samples, we're basically saying that we have a DG which is given by some kind of mean value plus a fluctuation term times the variance, and or square root, sorry, and so even though the mean is at a certain place, this term allows it to fluctuate wherever it wants within this constraint, and that this whole procedure doesn't take into account at all the surrounding points. So if the current gain is here, then it's unphysical for the next one to be here, and then the third one to be here, and so on. They are correlated. And so we need to take that correlation somehow into account. One way of doing this, which was done in Planck, and which was done in our first Beyond Planck release, was that we define a smoothing window where we where we basically say that the value of the point in the middle of this window is given by the average of all of the surrounding points. The size of the smoothing window varied, and the reason for that is that it varied depending on which PID we were looking at. The reason for that is that if we again have a look at this dipole pattern, the gradient of this dipole is in this direction. So this is the greatest variation. And when the Planck instrument scanned in this direction, then the typical data for a given PID would look would look very much like this. Would have these big dipolar variations. But the scanning strategy of Planck was such that it could shift this direction, and sometimes it would lie along this axis instead. In that case, the fluctuations were a lot weaker, which means that the statistical power in those PIDs for estimating the gain is also a lot weaker. Which means that what we basically see when we look at all of the PIDs, we see something like we have the small variations when the dipole is strong for the PIDs, and then the dipole becomes weaker and the fluctuations becomes stronger, and then you see this pattern regularly. And so what we did was for these areas, the smoothing window was allowed to be quite small, because the statistical power per PID was quite high, whereas for this range we had a larger smoothing window. And following this procedure, we got a gain that looked much smoother and looked a lot more physical. So that is one way of solving the problem of unsmoothed gains. Another way of dealing with the problem of unphysical gain fluctuations is the more Bayesian approach. So if you recall back to when we looked at the scalar gain factor when we tried to estimate that using data from a single PID, I said that the posterior of the gain given the data is proportional to the likelihood or the probability of observing the data given the gain. What that statement implied is that the so-called prior, which should also be part of this in the Bayes theorem, of course, is set to 1. Basically, we're saying that we don't know anything about the gain at all. And this setting the prior equal to something else than 1 is a very natural Bayesian way to incorporate extra knowledge about how the gain or how a certain variable should behave. And so in the case of the gain fluctuations, we will write up the same thing. And now we want to include a prior on the fluctuations. And this prior we're going to set equal to a normal distribution with a 0 mean and a covariance matrix G. I'm not going to go into detail here how to derive what then will happen, but if you look at the first Beyond Planck paper and the appendix 3 in that paper, you'll see the derivation of what I'm going to write here. You recall that the solution without the prior for the gain fluctuations was that we had this T matrix transposed. We had the noise and the T again times delta G I is equal to and then this residual factor. And then we added fluctuation term, which was the square root of T, like this. And this, with the introduction of a prior with this form, this changes into this equation. So we have this prior covariance matrix plus the old term. So this will also be specific to each detector. This term remains the same. That doesn't mean necessarily that the mode will, doesn't mean that the mode will remain the same, because this whole equation will be divided by, or we basically have to multiply the whole equation by the inverse of this term to find the actual sample. So the mode will be what we call Wiener filtered, which is that in areas where we have a high signal to noise, the data will be able to determine most of the solution, whereas in low signal to noise areas, this covariance matrix will dominate, and affect the solution of DG. And then we have a fluctuation term, which will be exactly the same as this on the left-hand side. And that's it. Now there is another way of writing this, which you will see in the paper, which is that this fluctuation term can be rewritten. So I'm just going to rewrite that particular part. So in this rewriting, we will have two, these are both normal vectors. I'm sorry, they should be vectors. So in this case, we're drawing two of these, both from a normal with a unity variance, and then multiplying this one with the square root of G inverse, and this one with with T I, and then the noise matrix to the -1/2, adding those two together. So if we set our delta G to be equal to this plus these two terms, you will end up with a sample which has exactly the same variance as if we use this term instead. And the reason we might want to use this equation instead of this has to do with computational efficiency. This is a system that must be solved using numerical methods such as conjugate gradient, because it's a quite large system. And it turns out that writing the fluctuation terms in this form makes that task a lot easier. So typically, in our case, this is what we use. And with this, we will draw a sample that that includes this covariance matrix, and which then, instead of being these very noisy fluctuations, will be a solution that still varies, but a lot smoother. A natural question to ask when we start now operating with the covariance matrix for the gain fluctuations is what exactly this covariance matrix is. And the gain fluctuations have their origin in the electronics of the instrument. And we know that the effects that arise from the electronics are typically due to the small changes in the properties of the materials that the electronics are made out of. And such fluctuations typically give rise to signals that follow whose power spectrum. So this is now the power spectrum of the fluctuations, not the probability distribution function. So that follows so-called 1/f spectrum. And if you've seen the lecture on noise estimation, you know then that the covariance matrix for the correlated noise, and in our case the gain fluctuations, can be written as bottom line fluctuation multiplied by so this is a function of frequency multiplied by f ni. So this is ni frequency that needs to be estimated, and then we have this this alpha. And so in principle we have three parameters that describe our covariance matrix, and these parameters need to be figured out somehow. So what we can do is to, after we have sampled our gain parameters, we can insert a sampling step where we sample these parameters. So alpha, f ni, and then typically with this is a parameter that follows from data or from something else. So we estimate alpha and f ni given sigma 0 and everything else. And this distribution is given in the same case as with the noise correlated noise by sum over frequencies of the power spectrum of the fluctuations divided by the matrix itself and minus the log of the matrix. And if we operate with some prior on alpha f ni, we can add that here, but typically this is the core. So using this expression, we can evaluate or draw a sample from this distribution either by splitting it up into two steps, where we sample alpha given everything, and then f ni given everything. For example, using an inversion sampler for this, and always using this expression for the probability density function. Or we can sample directly from this using something like a Metropolis Hastings sampler. By inserting this the step into the chain, we will estimate this covariance matrix as part of the whole Gibbs chain using our current estimate of dg. This is what enters into this evaluation. And so then we have all the steps we need to sample the gain, basically, in a smooth way. So, to summarize this lecture, we started looking at how a detector is measuring the CMB or something that has an intensity, and it spits out a voltage. And the gain factor is what converts between these. We also saw that this gain factor is not constant. It varies in time because of the electronics in the instrument. And so we have to estimate this factor continuously during the mission. We had a look at the degeneracies between G and especially correlated noise, and we looked at some methods for how to deal with this, and in general for estimating G better. The first thing we noticed or noted is that G is slowly varying. So instead of having G vary with the time or the samples itself, can vary only on the scales of the PIDs or the pointing periods, which last for, in the case of Planck, last for an hour. We also saw that we looked at what kind of properties our calibration sources should have. We found that the solar dipole and the orbital dipole exhibit some of these or these characteristics. Not both at once, but each of them has its strong point. So, and then the final thing we looked at was that instead of sampling P of G given N core, and then sampling N core given G, which gives which, when these two are degenerate, makes for a very slow exploration of the parameter space. We replace this with joint sampling of G and N core, and this we transformed into sampling G marginalized over N core, and then sampling N core given G, using a trick from probability theory. So so this step remained the same as it was, whereas this step we needed to now marginalize over the correlated noise, which meant more complicated matrix evaluation, because now the noise covariance matrix was both the correlated noise and the white noise. So we wanted to use these the dipoles in order to estimate the gain. So in order to do that, we let the gain at any PID and for every detector be equal to an absolute gain plus detector-specific gain that could not vary in time, and then this time-specific gain factor. And we estimated this using the orbital dipole, and these two using the total signal, which is very similar to the solar dipole. And we looked at how we could draw samples from each of these conditional distributions, which both of them had their own little quirks, but followed much of the same pattern. And we saw that this last distribution, when drawing from that and estimating the fluctuations, we got a solution that had a lot of small fluctuations that were not physical, because the gain typically moves on a slower scale. These were due to not taking into account correlations between data points. We explored two ways of doing that. The first one was to use these boxcar averages, so just average, setting this point equal to the average of all these data points. And then the second Second way of smoothing that we looked at was to, instead of just looking at the likelihood, we also included a prior for the fluctuations, and that prior for us was in the form of a normal with the covariance matrix, and we saw how that covariance matrix could be, or the fluctuations were follow the 1/f spectrum. So the covariance matrix is given by the same expression as for the correlated noise, and we also saw how we would estimate the parameters that make up this covariance matrix. So I want to thank you all for following this lecture.